All right, so now we are getting into more elective content. So for the last week of calculus here, we're going to do one brief topic a day. And on the first day, we're going to take a look at the method of partial fractions. Let's say we have to find the integral of 1 over x squared minus 3x plus 2. Now our instinct might be to say that the integral of this is just going to be the natural log of x squared minus 3x plus 2. But when we differentiate that, to verify that's the case, yeah, we do end up with the x squared minus 3x plus 2 in the denominator we're looking for, but then we have to apply the chain rule, and we need the derivative of the inside of the log in the numerator, which is not the same as 1 over this polynomial. So we are going to use the method of partial fractions. So step 1, we have to completely factor the denominator. In this case, x squared minus 3x plus 2 factors as x minus 1, x minus 2. So that is step 1 complete. So now for step 2, we rewrite one fraction as more than 1. So we take our 1 over x squared minus 3x plus 2. That's going to be the same as 1 over x minus 1 times x minus 2. But then we can break it down to have one unknown integer over each of these two factors. So we've written it this way. And as long as we have linear factors down here, we can have constants on top. If we have, say, an x squared plus 1 in the denominator that we cannot further factor, that has to be under a numerator of 1 less degree. So if you cannot break down a degree 2, you must have a degree 1 numerator. If you cannot break down a degree 3, you must have a degree 2 numerator, and so on. But this would be convenient. We can easily factor a over x minus 1, or sorry, integrate a over x minus 1. We can easily integrate b over x minus 2. That'll just be a times the natural log of x minus 1 plus b times the natural log of x minus 2. But in order to make use of that, we have to know that we have values of a and b that work. We have to find something that can get that job done. So that will be our next step. So we take our 1 over x minus 1, x minus 2 equals a over x minus 1 plus b over x minus 2, and we set up a linear system to solve for a and b. So that linear system we get by multiplying by all of our denominators. Our left-hand side becomes 1. Our right-hand side becomes a times x minus 2 because the x minus 1 canceled. And b times x minus 1 because the x minus 2 canceled. Now when we multiply these out, we get ax minus 2x plus bx minus b. So this doesn't look like a system of equations. Oh, sorry, there should be, that's not an x here, that's an a. My apologies. But, so this doesn't look much like a system of equations. But if this is going to be true, it has to be true for every possible x across the entire real axis, or at least through the entire domain. So what we can do is set up two equations. One for the coefficients of x. 0 equals a plus b, and then another for the constants. 1 equals negative 2a minus b. So our first one leads us to the conclusion that a equals negative b. If we put a negative b where the a is, then our constants will tell us that we have a 2b minus b, or b is equal to 1. Linking this one back to the start, which means a would be negative 1. So is that true? Can we verify it? When we go back to our first definition, a is over x minus 1, b is over x minus 2. So if we have negative 1 over x minus 1 and 1 over x minus 2, if we put these all over a common denominator, negative 1 times x minus 2 is negative x plus 2. And then to that we add 1 times x minus 1. Our x's cancel. Our 2 and our 1 combined. And yes, we do get our original 1 over x minus 1, x minus 2. Which means the integral of 1 over x squared minus 3x plus 2 dx is going to be the integral of negative 1 over x minus 1 dx plus the integral of 1 over x minus 2 dx. Or the negative log of x minus 1 plus the log of x minus 2, and then we always add our constant c. So this is how we can handle integrals over polynomials of degree higher than we're used to. We break them down into separate fractions and combine them with the method of partial fractions. So coming up tomorrow, we are going to look at Newton's method for some numerical solutions to root finding.